Okay, so question 6. We have a situation that states that blood flows through an artery of length 3.4 centimeters and diameter 2.1 millimeters. It then encounters a blockage, reduces the diameter of the artery to 1.9. The length of the blockage is 0.25 centimeters. If the blood flow rate is 400 mils per minute, what is the pressure difference across the entire 3.65 centimeter length? And we're given a blood viscosity. So again, it's a viscous fluid flow or a non-ideal fluid flow question. A pretty challenging one here in that we're going to have to consider a sort of a vessel of length L where there's no blockage, where there's a given delta P, and then another vessel shorter length has a delta P, and then consider the delta P across the entire total length. So again, I'll try to draw a picture here of the situation. So we've got this wider one here, and then we're going to consider some sort of blockage and have a shorter length. Again, it's not drawn to scale. I just want to sort of indicate give this a sort of a picture. Okay, maybe the walls built up some plaque or something, and it sort of narrowed the artery, so across this, we're looking for the pressure across the entire length. So let's add a couple of things in here. So things that we do know. So if I think about, we know the blockage is 0.25 centimeters. The length of the healthy piece, normal piece, is 3.4 centimeters. So look, that gives us the entire 3.65 centimeter length. We know its diameter over here is 2.1 millimeters. This diameter over here is 1.9. So again, I didn't draw this to scale. This is quite handy. And we know the flow rate is 400 mils per liter. So another 400 millimeters per minute. Excuse me. So another awkward unit. Okay. So for this type of question, or any kind of question that looks like this, you have to apply Poisson's equation twice. So Poisson's equation can only tell you the delta P across a length of pipe of a fixed diameter. So I'll call this points A and point B. So we could use Poisson's equation to figure out what is the pressure difference between A and B. Zoom in here for a second. And then we could use it again, if I call this point C, to figure out what's the pressure difference between points B and C. Now, what I hope you can sort of consider here is that the delta P, we're trying to figure out the delta P A to C is going to be equal to the pressure difference between A and B plus the pressure difference between B and C. Hopefully you can see that. So A to B plus the delta P of B to C. Okay. That's how you sort of solve this problem. Since we're in a sense you have to use Poisson's equation twice. That's sort of what I mean by twice. There's two different delta P's we have to figure out, and then sum those delta P's to figure out the entire pressure difference. Okay, so if you look at review question 5, we can write these delta P's in terms of the diameter. So with this delta P A to C, this is going to be, we can write this as Q times 128 A to L, A to B, over pi, then D, A to B raised to the 4. The flow rate does not change. That's what we have to assume. This is laminar flow. Again, 128. The blood viscosity, assuming it doesn't change due to the blockage. Then L, B to C, all divided by pi, again, D B to C raised to the 4. So even at this point it's still a pretty challenging question because it's a lot of terms that have to be added up and lots of factors that need to be converted. So I'll do that sort of in the space over here on the right, just underneath the percent of choices. So the Q is awkward, so we start with that term. That's 400 milliliters per minute. So a milliliter is only 1/1,000,000th of a cubic meter. So there's 1,000 millimeters in a liter. There's 1,000 liters in a cubic meter. So this will be 400 by 10 to the minus 6 cubic meters, and there's 60 seconds in a minute. So this should give you 6.67 by 10 to the minus 6 meters cubed per second. So let's get the correct flow rate. Our eta is, luckily that's it in the correct unit, 2.5 by 10 to the minus 3 Pascal seconds. The length of A to B, 3.4 centimeters, is 0.34 meters. The length of B to C is going to be 0.25 centimeters, so that's going to be 0.0025 meters, or 0.25 by 10 to the minus 2, or 2.5 by 10 to the minus 3, whatever way you want to work that out. So that's the two lengths. The only thing that are left are the diameters. So the diameter of A to B is 2.1, so that's 2.1 by 10 to the minus 3 meters. And then diameter of B to C is 1.9 by 10 to the minus 3 meters. Okay. Alright, so you can see all those. And they're your terms that are in each of these. So once you sort of figure out those values, delta P A to C, this first term is definitely the one more significant. Same flow rate, but the length is longer, and so the diameter is we only do just the diameter, and even the length being significantly longer, more than a factor of 10. So this I end up getting 1187 pascals, and the pressure difference across is much smaller length, but even though it has a diameter, so the diameter differences are not significant, even though they're raised to the 4. I believe that the length is playing a significant role here, and this gives me 130. So the sum of these two give me 1320. So that's the entire pressure difference across the entire 3.65 centimeter length, or that these are the ones across the individual pieces, the sort of healthy non-block portion plus the delta P across the block portion. So that should give you choice E as the correct answer.